my wonderful AP Chemistry students. We are returning from our break with topic 8.5. This will be a good one because truly this is actually all review, if not review from this year even. And so this will be a nice way to kind of like ease ourselves back in after break. Thank you guys for your understanding with this video getting out a little bit later. I apologize dealing with that family emergency, so I appreciate you all and your understanding. And please don't forget that our next class, we're going to be doing a short quiz on topic 8.4. So look through those example problems that we did so you come prepared, because that quiz is going to come straight from those example problems. I don't even think I'm going to be changing numbers. Maybe I will change numbers, but the questions will be exactly the same. Okay, so this topic has everything to do with titration. Okay, and that's when we have an acid and a base and they're going to react and they're going to neutralize each other. Okay? And one way that we do titrations is when we find an indicator that the endpoint changes color. Essentially when the endpoint equals the equivalence point. So equivalence point is when the moles of the acid equal the moles of the base. Okay, this is the equivalence point. Now, if we look at all these different titration curves, and you've seen these before. Now, if the pH is starting off really low, that would mean it's a strong acid. And if the pH is ending really high, then that would be a strong base. So there must have been a strong acid down in the Erlenmeyer flask, because that's the thing that we're measuring. Okay, this is our analyte. And then our titrant is what's in the burette that we're dripping in there. So the base must have been dripping into this acid, because very slowly this pH starts to increase, then it drastically increases, and then we get to this point where it's primarily a base that's inside here that we've added. The equivalence point is right at that like halfway spot where it kind of where it becomes more vertical. Okay, so if I look at this and I go, okay, what's roughly halfway in between there? That's the equivalence point. That's where the moles of the acid equal the moles of the base. Now, when it's a strong acid that's being titrated with a strong base, the equivalence occurs at a pH of 7. Now, on this next one, though, we still have a strong acid, but see how the pH doesn't end very high? So it must have been titrated with a weak base. So then if I look at the equivalence point here, so halfway in between on that vertical area, notice that this is below 7. The moles of the acid, right? That's the equivalence point. The moles of the acid equal the moles of the base. I have my kids with me, so if you hear them in the background, I apologize. Now, this makes sense that the equivalence point would be below 7, because we're saying that the moles of the acid, the moles of this acid, which is strong, is equaling the moles of the base, which is weak. So if we have a strong acid, equal amounts of strong acid and a weak base, then our pH would be on the acidic side. It would be below 7. Here is a weak acid being titrated with a strong base. And again, if we look at this equivalence point, it is above 7. And then we have a weak acid being titrated with a weak base. That's when our equivalence point returns to 7, but you can tell that it's kind of harder to see that equivalence point. And the best titrations are when we pick a dye that changes, an indicator that changes colors at the equivalence point. So if it's a strong acid and a strong base, I want to pick an indicator that changes color at a pH of 7. But if I have a strong acid and I'm titrating a strong acid with a weak base, then I want to pick an indicator that changes colors at a lower pH. There it goes. It's off.
I just need to find it.
Okay. So That's what the endpoint is. The endpoint is when the indicator changes color. Indicator changes color. Okay, so in AP Chemistry, and probably in a lot of chemistry classes and other scenarios, they would assume that these things are the same. Just because, like, if we chose a bad indicator, they wouldn't be the same, but we're going to make the assumption that we chose a good indicator that changed color at the equivalence point, okay? So anytime someone says end point or someone says equivalence point, we can use those interchangeably. Like, we can assume that one means the other. Okay. So, what's going on? Let's start with an equation. So it looks like we have a strong acid here, okay? Excuse me. So the strong acids have hydrogens in the front of them. I'm just going to do an HA for the strong acid, and then I'll do an example underneath this, like hydrochloric acid's really common, HCl, okay? So the A is a placeholder for the other part of this acid. And these are aqueous, they're floating around in solution. And we know it's being titrated with a strong base, okay? So we have our strong base, which is a group 1 or a group 2 metal with hydroxide. And so an example of this is sodium hydroxide. That's probably the most common one. But again, this B is just being a placeholder for us. This is going to be aqueous. Okay. And now, this is going to break apart. Sorry, these are going to react. And the H plus is going to break apart from the A minus, and the OH minus is going to break apart from this B plus here. And so what you end up with is water, liquid, okay? So again, that came from this hydrogen and that OH. And then a salt, water and salt, okay? Now, if this salt is soluble, which it usually is, then that would be aqueous. So like our example down here is going to be H2O liquid, and then this would be table salt, sodium chloride. Okay, now I'm going to focus on just the acid part of this for a moment, because you know how this would break apart, like if it's aqueous and it's an ionic solution, like then it would break apart into a B plus and an A minus. So for this part, because I'm looking at this acid here, I'm going to concentrate on this acid breaking apart into H plus and this A minus, okay? So how many should I choose? Let's do 6. That'll be helpful.
I need a rock.
Go see what you can find, dude. So at this point, I have solely acid, okay? So like, let's just do HA 1, 2, 3, 4, 5, 6, okay? So we have this acid here, okay? And it's going to start to react. Now I want you to think about this for a minute. We know the equivalence point is when the moles of the acid equal the moles of the base, okay? Like if I come up here, here's my acid, here's my base. Now if I have equal amounts of acid and base, this is a one-way arrow. These are gonna completely react, and they're gonna turn into water, and then this like B plus and this A minus that's floating around in there, okay? So the all of this gets consumed if there's an equal amount of base. So like if I have equal amounts of this and this, I have 6 of these and 6 of those, they will completely react to form these things. And so what's really interesting is at this point, we have equal amounts of the acid and the base, and it completely reacts. And so what we are left with, all of these hydrogens actually went to water, liquid. I'm not going to draw the water liquid. And what we're left with is those A- that are floating around. That's what's going on at the equivalence point. All of the acid that we started with has reacted, and that all the hydrogens have been reacted with the base and formed that liquid water, and what we're left with is A-. And so that occurred at a certain volume, right? That's the equivalence point volume. Well, we have this really interesting point, and it's called the half equivalence. So this was the equivalence. Now, if you look at whatever the volume was, like let's just say hypothetically it was 10 milliliters. So then if we go to half of that, if we go to 5 milliliters, this is the half equivalence. Okay, this is the half equivalence point. And at this half equivalence point, something really interesting happens. The moles of the original acid, so let's do half of them have reacted, and the other half are equal to the conjugate base. Okay, so this is where the moles of the acid equals the moles of the base as far as like this goes, that it's being titrated with. And at the half equivalence, half of that original acid has reacted, half of it still remains. And we know that when we have an acid and it breaks apart into something else, that something else is its conjugate base. So this is when the moles of the acid equal the moles of the conjugate base, okay, not the base that it's being titrated with. And the reason why this location is really helpful is because the pH at this point, so in this scenario, 1, okay, so the pH of 1 is equal to the pKa. Okay, now I want to make sure I'm phrasing that correctly, so let me just double check. So pH equals Yep, exactly. So that's where the pH, so at this point it was 1, is equal to the pKa. And so where this can be really helpful is when you're given one and you're asked for the other, then you can actually use the titration curve. So like let's say they showed you this titration curve and they asked what the pKa is, then you would find the half equivalence and then you would go over and you'd be like, well, the pH of the half equivalence is 1, and so then that must equal the pKa. Just a reminder, if you then needed to solve for the Ka, you would do 10 raised to the negative pKa, and that equals your Ka value. Okay, let's keep going. All right, same idea here, but now we're going to be focusing on the base. So, with this base, and we've seen this like reaction before with water and a base here. It's like when we're doing our weak bases, where it's like we would take this weak base and it would react with water, liquid, and then that would turn into the B H, and it left hydroxide. Okay, and so it's an odd little switch here, and I'm kind of tempted to almost write it opposite from this because we have sodium hydroxide, but this is like our base, and then this is the conjugate acid, and that makes sense because we have the hydrogen, right? Like if I rewrote that, put the hydrogen at the front of it, that's where these hydroxides come from, okay? So at this point, similar to what we had seen before, but we're starting with like only base. Let's do 6 of them again. Okay. And at the equivalence point, we know that the moles of the base equal the moles of the acid. So this is what I was telling you before, that it's going to completely react, that all of the base that was initially there is going to turn into its conjugate because we have equal moles of acid that we're titrating this base with. So it's going to cause all of that base to react. And so what we're going to be left with at the equivalence point is just its conjugate acid. And so, just like before, if the equivalence point occurred at 50 milliliters, go to half of that. This is the half equivalence point. Half equivalence, okay? So at the half equivalence, something really cool happens, just like we were saying before, that the pH is equal to now. This is a base, though, that was being titrated. And so... Okay, Mom will help you in a little bit. The pH at this point is equal to the pKb. All right, so be careful when it's a base. So it's not our pKa, it's a pKb. So it looks like maybe it's at 12 or at that point around there. All right, wonderful. And like we said, this is where half of the original base is there, and then half of it has reacted and turned into the conjugate acid. Okay, great. Now, I had showed you a trick with this, but we're going to reiterate it. Okay, and this is wholly based on the idea that during a titration, we're trying to reach the equivalence point. And we know that at this equivalence point, something really important happens. The moles of the acid equal the moles of the base. Okay, now one important distinction here, this is not necessarily, if it was a strong acid and a strong base, then this statement would be true, but it's not always a strong acid and a strong base. That does not always mean that the moles of H plus equals the moles of OH minus. That's not necessarily true. It means the moles of the acid equals the moles of the base. Okay. Now we have, we're often given volumes and concentrations, right? Like if I'm given the molarity, the concentration of something, that's going to be moles over the volume in liters. And if I rearrange this to solve for moles, it'd be volume times by molarity equals the amount of moles. Okay. Now at the equivalence point, we know that the moles of the acid, so like let me say the moles of the acid, that's got to equal the moles of the base, right? That's what the equivalence point means. So instead of saying moles of acid, what if we replace it with volume of the acid, molarity of the acid, right? That's the same thing as moles of acid. I just proved that right here. And that will equal moles of the base. But what if we replace that with volume of the base, molarity of the base, concentration of that base? And then whatever we're given, it's like an M1V1 equals M2V2, right? That we can rearrange and solve for any of these as long as we're given the 3 other items. But please, please do not forget that this equals the moles of the acid, and this equals the moles of the base. So if they ever just give you that number, you don't need to multiply the volume and the molarity because they've already provided the moles. So we're going to end this video by doing a couple of examples, and then we'll just keep working through those examples when we get to class. So I have 31.25 milliliters, 0.250 molarity hydrochloric acid, HCl. So this is my acid. So my volume of my acid. Now, if you're dealing with 2 volumes that are the same units, then you don't have to change their units. But I need you to be really careful because there are absolutely scenarios and equations where you have to change it to liters, and this is one of the few times that you don't, but it's not going to give you the wrong answer if you do convert it to liters. And so out of habit, I find that I just convert them to liters, and that way, no matter what the scenario is and which equation I'm using, I know that I'm okay, that I'm not making a mistake by leaving it. So like this one in liters would be 0.03125 liters. So there's my volume of my acid. And my concentration, my molarity of my acid is 0.250 molarity, okay? Was titrated with an unknown concentration of sodium hydroxide. Okay, so it looks like we're going to be finding this concentration of hydroxide, and hydroxide's a base. We see that hydroxide OH at the end there. So we're going to be solving for this concentration of the base. The end point was reached. Now that's important because this justifies, this end point justifies that the moles of the acid equal the moles of the base. And this is so important, people. I need you to write this down when you're doing a free response question. You can't just jump into MAVA equals MBVV. Like, you need to justify why you're making that choice, and this is your justification right here. That's what you need to do. You need to say, hey, we're at the end point, and this is when the moles of the acid equals the moles of the base. So that's why I can say molarity of the acid, volume of the acid, because that equals moles of acid, equals molarity of the base, volume of the base. Okay, let's keep going. When 32.75 milliliters of sodium hydroxide is added. So the volume of the base is equal to 0.03275 liters. I'm going to rearrange this to solve for the concentration of the base. So we just have molarity of the acid times by volume of the acid divided by volume of the base equals molarity of the base. All right. Plug this in, 0.03125. Now